We are back once again for daily LeetCode. Did you do your LeetCode today? And if you haven't, ask yourself, why not? Whomst is to blame? Honestly, the people that are to blame are the people at LeetCode. Now, I'm joking, but we're back once again, okay? And I'm wearing the Wumbo sweater because you got to turn it to Wumbo. So, we're back once again, and I've been doing some thinking. I mean, the LeetCode is going well, and I think there are just some benefits to daily work. And the benefits, we got one of those benefits yesterday. So every little while, right, we'll get stumped on a problem, we'll work through it, and then we'll receive an incredible it's not even a dopamine release, because dopamine really is the anticipation. It's really more about anticipation. But this one is more, it might have to do more with relief. And sometimes relief is a reward in and of itself. I think there's a I don't know if it's a parable or there's a story, but pretty much about a man who carries a stone, and he carries the stone everywhere he goes for as long as he can and as hard as he can, and it's merely for the sake of letting the stone go. And the reason he does this is because there's so much relief in holding the stone for so long that when he lets it go, it's just an overwhelming amount of relief. And he does this over and over and over again. And the question to ask ourselves is he delusional? Is there any meaning in finding a stone to holding it until it gets, holding it until it is, until you can't hold it anymore, and releasing it, right? And I think there is. I mean, that's pretty much anything I imagine that has actually been worth it has been like that. Granted, you never ever really release the stone, but it just goes to show that there's some specific brain wirings that we have to abuse. One of these reminds me of, there's something called opponent process theory, and it's pretty much, there's like two, and it comes to I think it has more to do with addiction, but there are like two processes, right? And you have an A process, and these processes basically work as the inverse of each other, right? The brain is always trying to reach a homeostatic level, and even the body is always trying to stay at 99.8 or 99.7, whichever one it is. And with the brain, basically, you can never be always happy, because happiness or sadness is most of the time derived as a difference between, it's like a relative difference, right, between some sort of baseline and where you currently are. And basically, the opponent process theory states that for every A process, there's a B process for regulation. So if you experience an overwhelming high, right, there should be a B process for of regulation, of down regulation back to some sort of baseline. And this is pretty much a broke man's version of breaking apart these things. And the same thing would be the backwards version, right? If you experience a huge amount of some sort of down regulation, there should be an upwards regulation as well. The interesting part when it comes to addiction is that you might do something like, let's just say you're interested in, you need something addictive. Like, let's just say scrolling, right? The worst part, right, is that the more you do something for the A process, like the dopamine you get when you're anticipating the next thing you're about to scroll through, right, that reward gets shorter and shorter and shorter, right? You're not going as high, but the B process gets stronger and longer. So in the beginning, it might look like this, A, B. In the future, it looks like this, A, B. And the next one, A, B, A, B. And you just kind of keep going and lowering and lower and lower. All this to say, it can be reversed, which is pretty cool. And when I think of this, I think of people like David Goggins and other people who do this stuff where they torture themselves. And they basically, and it's just a really convoluted way for long-term contentment, I think, is to flip the thing. If it tastes good in the beginning, not always. There's not like things that are stamped into the future, but generally, if it tastes too good in the beginning, it's usually not going to be very rewarding in the end. And I found that with so many different things. Like sometimes I'll receive a Christmas gift, and some of the ones that I'm so excited for in the beginning are the ones that I forget the quickest. And the ones that I wasn't so excited for are the ones that I actually like still use and think about. Or whenever I get a new game and I'm super excited to play, and I'm like, oh my God, this game's going to be the best game ever. I'm not playing that game a week from now. But the game that I'm like, is this fun? I can't tell. I'm still playing those games. And it's pretty convoluted, but all this to say, just like David Goggins and all these people who do these really, really, really torturous things, makes people wonder, like, why would one do those things? And I think it is just the flip of the process, because you can imagine, right? If your B process always gets longer as a result, if your B process always gets longer as a result of your A process, imagine this: if you torture yourself, then your upregulation is actually very rewarding. So if you go like this, your B process would take you higher for longer. And it's actually a really interesting thing. And I think it's very interesting to see that most of the people who seem to have found some sort of long-term contentment, joy, or life-satisfying measurement seem to all do very similar things. It's usually some stoic activity that they've dedicated themselves to, or it's something that is very, very difficult and they're working towards some end, and it's always difficult. And I think that just goes to show it's just interesting. Natural agents are just so interesting, aren't they? They are just very interesting. You can imagine how this, even from an evolutionary perspective, might be very useful for a populace of apes. We are completely off the rails now, and I don't even know what I was talking about in the beginning, but we are back for LeetCode. And yeah, I forgot where I was going with all this. I just be saying stuff sometimes. So we're actually very, very short on time today, so we're going to do 2 short sessions. One session is going to be about LeetCode, and one session is going to be about game dev. I have no idea which channel I'm going to focus more on in regards to how the upload schedule works. I would like to do more game dev content. I would like to do more LeetCode specific content. At the same time, posting both of these on the same channel, it seems a little bit nonsensical. They're both sort of programming related, but I just had different ideas for both of these black channels. So maybe the wave will just have to be, maybe the wave is just going to have to be, I've uploaded this on upload on separate channels, but you should check out the game dev channel, which is in the description below. So we're just going to jump into it then with today. And we do actually have some comments, which actually I might save for the game dev channel, actually. So I think that is what we're going to do. And then we're going to have 30 minutes that we do today, and then I'm just going to start the timer because we already know what it is. On Fridays we do a shorter session, and it just is what it is. So it's not something we can really stop. But we also had a great release yesterday, so we're going to try last stone weight. So you are given an array of integers, stones, where stone sub I is the weight of the ith stone. We are playing a game with the stones. Stone sub I is the weight of the ith stone. We are playing a game with stones. On each turn, we choose the heaviest 2 stones and smash them together. Suppose the heaviest 2 stones have weights x and y, with x being less than or equal to y. The result of the smash is, if x equals y, both stones are destroyed. X does not equal y, the stone of the weight x is destroyed, and the stone of weight y has a new weight, y minus x. At the end of the game, there is at most 1 stone left. Return the weight of the last remaining stone. It looks like we just have to do exactly what they say. So each turn we basically smash the 2 largest stones together. So here we'd have 8 minus 7, which would give you 1. Right, then we'd have 4 minus 2 to get 2, right? And then we'd have 2 minus 1 to get 1, and then looks like we might, and we'd have 1 stone left. This is definitely giving me heap vibes. Oh no, maybe not heap vibes, because you want to get the, oh yeah, well yeah, it would give me heap vibes actually. I'm pretty sure if we check related topics, yeah, we'll get a heap priority queue. I actually don't know how to use a heap, so maybe this is one where we can look into that. What's the underlying data structure for a heap? Is it a BST? Because we might just try and implement one. Underlying heap data structure. Because we could implement this with a stack, but the issue would be that when we reinsert a stone, the elements we can have a min stack or a max stack, but it kind of requires that the elements at a particular point in the stack when we set them up don't change below them. Is a heap not just a BST? I mean, we can do this without a heap. Isn't a heap just a BST? Or a heap would give you the number you're looking for in what sort of time? It says a heap property. So maybe we could just powwow on what a heap property is. This might just be a chance for us to learn about heaps. Because we could just implement a heap, right? And then we could just run get, right? Get both largest, right? Smash together, modify array. Yeah, actually no. We could just get both largest, smash together, right? Add back to heap, and then once the heap has when it has 1 or no elements left, we'll stop. But you can do it without a heap. I'd like to do it with a heap, but that would require us knowing exactly what a heap is. I mean, I know what a heap is. It's basically some sort of data structure that allows us to get the min and max element in ideal times. But I guess I'm not really understanding the difference between a heap and a BST. Apparently, A heap has a worst case time complexity of log n. So we have an insertion, deletion, as well as searching. We could also do this in worst case n squared time. Yeah, I think it's clear we could do this with a heap, but maybe we'll just do it in n squared time. I'm kind of thinking here, if we can solve a problem without a heap, and the time complexity is not that much worse, we do n squared versus log of n. Wait, actually, n squared versus n log n is pretty crazy, but still, it doesn't seem as bad. So maybe it'll be okay, and yeah, maybe it'll be fine. So, maybe we'll hit the button anyway. And yeah, so with n squared, I think we can just do one linear time iteration through to find two of the biggest numbers. And then we'll just smash them together. And then we'll do one last search through to find. Well, actually, are we guaranteed that each element requires one smash? I think that would work. Because at each time we lose at least one element. So yeah, I think worst case would be n squared. We'd smash them together, figure out the two largest elements, and then we do one last linear scan. Last linear scan to determine end. Last stone weight. So yeah, I thought we might need to do the whole I thought maybe it made sense to do the whole like heap thing. Maybe it doesn't make any sense. I mean, to force ourselves to do it if we can figure out a solution that where we don't have to do it. Do we need access to the indices here? We do. We'll do stones dot length I plus plus, and then we can duplicate this here, change this to m, and we'll have a first max equals negative infinity, and then we'll copy this and have a second max, and then we just need to find which value the two largest values can be the same, so we can't do this based off of value. We'll do it based off of IDX. So first max IDX will be equal to 0, and second max IDX 0. This will be equal to 1. I think we can actually stop at stones.length minus 1 to get the first max. We would just pretty much do like, right, first max nums sub first, so stones sub first max IDX is greater than stones is greater than stones sub m, right? Then first max IDX becomes m. But we have to make sure they're not the same. So let's say first max IDX does not equal second max IDX. And and stones sub first max IDX. Stones sub first max IDX is greater than stones sub m. Let's say first max IDX equals and we're actually going to do second max. Yeah, we can copy that first portion here, but we're actually going to change this to second max IDX since this is going to be working kind of ahead. So I have 2 and 7, right? 7, their indexes are separate, but 7 is greater than 2. So we're not going to do anything, right? And then we have, we'll be starting at 2 for first max, right? And 2 is not greater than 2. I think what we want is, right, 2 it's if the number is less than it, then we would take it. If our current number is less than it, then we would update our number, right? And then here we'd actually change second max IDX equal to m, right? 2 is not less than 2. 2 is less than 7, but maybe you can't do this in one pass. Maybe you cannot do this in one pass. Now that I'm thinking about it. Because we wouldn't choose 7. We wouldn't choose 7, even though we should choose 7. I guess it would technically still be n squared time if we do it this way, but the runtime complexity would still be pretty crazy. So we don't have to do any of this first max, second max stuff. We'll just say first max IDX is less than stone sub m, then first max IDX equals this value. And then we'll include every number here, and then you could just do another loop. Here we'll make sure that first max IDX is not equal to second max IDX. And stone sub second max IDX is less than stone sub m. Then we'll say second max IDX equals m. Now you have the two largest stones. Actually, these should have a order that already means we can subtract them from largest minus smallest. It should be able to just do stone sub first max IDX equal stone sub second max IDX, and we'll push this back up to the front, right? And if they're equal, I think they said they should both become 0. Both stones are destroyed, so stone sub first max IDX would equal 0. You can copy this. And then from here, we just have to do the subtraction. So second max IDX would equal 0, and we would give this the value of stones sub first max IDX minus stone sub second max IDX. And then we'll just return 0 and then print stones, but it should just have one number left in it. So our array is completely empty. Something interesting is happening here. So I'm going to print both of the stones something is wrong because I'm getting both numbers are the same every time, but they literally should be impossible for them to be the same number. Because this one says if first max IDX does not equal second max IDX. So once we find the first max, we set it equal to some value. Something is strange here. Oh, they start at the same value. So they can never... Wait a second. This is actually crazy. I'm actually not understanding how it's possible that we're getting two of the same stones. We get the same index, right? So we remove 8, and then we pretty much end up with all zeros. How are we ending up with the same index? When we explicitly say that first max IDX does not equal second max IDX. Let me just print this part out, I guess. Wait, I'm actually so confused. If index 4, index 0, four, 0. Oh, I think I finally get it. We're not skipping the number. First max and second max IDX will never be the same. Well, they can be the same. The issue that we're trying to skip is that M does not equal first max IDX. Right. Basically, what we were doing before was saying that these two IDXs had to be different to update them. And that's fine. But what it's being compared to is stone sub M. So we should be able to end this by doing one more last loop through. And in the last loop, we'll just say if stone sub M does not equal 0, then we'll return stone sub M. And we just add one more. We just add one more case. If we start them both at 0. That little part we spent so much time figuring out why it wouldn't update took a lot of time, but we can figure this out and just update our solution if we had just a bit more time. But we have to stop here for today. Fridays just have to have a shorter session because we're strapped for time, but GG.